Hey gang, don't mind, it's just me again. Okay, so today we want to talk about electrolysis. And electrolysis, lysis really means the splitting, to split something. And electro, of course, implies the thing that you're going to use to do the splitting is some sort of electric potential. Okay. Now there's two varieties. Let me just highlight this because then I can feel better. There's two varieties of that we're going to talk about. One is when we're talking about molten binary salts. Okay, and I'm just going to flip the page because I want to highlight the other one. The other one is the electrolysis of aqueous solutions. Okay, now they're similar, but they're in some ways quite different. The first one is really quite easy, but before we get into the nitty gritty of it, there's some notation that I think you should be aware of because it's going to help you in solving some problems when you're given. Often you'll be given a diagram and asked to explain what will happen. And so one of the giveaways is this right here. This represents some sort of direct current. Okay. In other words, a flow of electrons. And this notation, we have one long bar and one short bar. The short bar is meant to indicate the negative end of the cell or the source for direct current. So this is always the negative, and this is a positive. And so if you ever see that, what that means is that electrons are going to move in that direction. So this is an important part of it. So electrons are going to be moving in this direction. Now, in this first one, we're looking at the binary salt that we're looking at, as you can see, is sodium iodide, or I'm sorry, sodium chloride. So sodium chloride, just table salt, but in this case it's molten, which means that it has undergone an intense amount of heat, and we put in two electrodes. These will be just carbon. Carbon electrodes are not reactive themselves. They just are a place for electrons to travel from and to. And so the negative electrode is called a cathode, which is kind of funny because cations are positive charges. So the cations will go to the cathode. Why is that? Because they are negative. These develop a negative charge, so they're attracted that way. Okay, and at the same time, the chloride ions are going to be attracted to the positive anode, and where they will give up their electrons. So these electrons that you see here, maybe I should do that in some other color. These electrons here will end up being transferred around this way, and will create a negative environment here. The sodium ions, positive sodium ions, will be attracted to it, they will accept their electrons and become neutral sodium. So basically, what we're doing here is we're taking molten sodium chloride and we're breaking it up into sodium and chloride ions. Now, all we want to do with this is we want to figure out, number one, what is going to happen and how much energy would this take to do it. Up to this point in time, we've been talking about preferred reactions and the like, and those are all things that will happen by themselves. They'll actually produce, or if it's not a preferred reaction, not produce a current on its own. When we're talking about electrolysis, electroplating, and electrorefining, these are all situations where we actively put energy in to create a process where we'll get something out of it. Okay, so what's going to happen here? Well, we can almost figure it out on our own what the half reactions are going to be. We know that we're going to let's take the left hand side and the right hand side. So the first thing that's going to happen, use black, is we're going to have on this side we're going to have sodium ions, and they are going to join up with an electron, and they will make NaO, like that. What's going to happen here is the two chloride ions are going to give up their two electrons and produce chlorine gas. Okay? Now, what we want to do is we want to figure out what are the half cell reaction potentials for these. So sodium is way down the bottom, I know that. Okay, here it is, I found it. So EO for sodium is negative 2.71. Okay? For chloride, where is that? Okay, chlorine is way at the top here. You can't see it. I should put this in. It's way up here. So if we were going to add two electrons to diatomic chlorine and get two chloride ions, it would be plus 1.36. But we're not. This is going to be the oxidation process, so we're pushing it back this way. So that means that I have to change this number to the negative. So EO is negative 1.36. So the E cell is going to equal the sum of these two numbers, and I don't have my calculator, so I'll have to do it the long way. 704.07 negative. So this negative is in answer to this question: how much energy must be applied to make this go? That's the answer right there. Overall reaction is, if we were going to balance these of the electrons, so this would become 2, this would become 2, and this would become 2. Now, a mistake that a lot of students make is that when they double these, they feel that they have to double these, and that is not right. Do not do that, because what this represents is the amount of energy per electron. Okay, so it doesn't matter if you double the number of electrons. That's the electron voltage, the voltage for an electron. Voltage is a measure of how much work something can do. Okay, so don't double it. Okay, so this, I'm going to put a little notation here. Double this, to balance electrons. Don't double this. Okay. So I really need to get myself a ruler because this is getting really stupid. So here's my trusty memory board again. And these cancel out. So we have 2Na plus 2Cl minus goes to 2Na plus Cl2. Okay, so you're going to get sodium formed and you get chlorine formed. Okay, now that wasn't too bad, was it? Seemed pretty easy. I'll let you finish copying down while I have some of my coffee. See, I've got my coffee with me. Okay, you can pause this. If you ever want to pause this and just finish copying notes, you can. Okay, let's try a problem. This is on page 238 in Hebden, and I will pull it out of my so I can see it. Okay, so this is page 238, number 64. It says, for each of the following molten ionic compounds, show the half-cell reactions which occur at the cathode and the anode, the overall reaction, and the minimum voltage which is applied to make the electrolysis reaction occur. In other words, do what we just did. Okay? So I want you to do the potassium bromide one right now, and excuse me, we'll pause the video, try it out, and then when you come back, I'll give you the solution from my end anyway. Okay? Okay, pausing now. Okay, I'm going to assume you have paused and completed. So this is question 64A, and we are going to go after potassium bromide. So this is molten. So now we've got this in a container. We've got the electrodes. So, and this is, we have potassium ions, and we've got bromide ions. Okay? And so this is the negative side, so that's the cathode. This is the positive side, that's the anode. And so when electrons are going to go through here, we're going to see potassium go here and bromine go here. And so what's going to happen, we can see right away that this side, which is going to be on the cathode side, so this is going to be reduced and cared. So we're going to have potassium. Oh, I should do this in black so you can see what's going on. So you have potassium plus an electron. It's going to go to KO. And what does it say? Where's my table? What did I do with my table? What did I do with my table? Nope. Nope. Nope, 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 nope. What did I do? Oh, here we go. So K is going to be at the bottom too. Yeah, there it is. So K is way down here. It's negative. AO is negative 2.93. Okay. And the other thing that's going to happen is you can see bromine is bromide ion is going to give up its electrons. But in order to do that, you're going to have two bromide ions. and they will produce diatomic bromine and give up 2 electrons. Okay? Now that's going to be way at the top. Where's bromine? Yeah, there we go. 109. So if this thing was being reduced going this way, then it would be plus 1.09. But what we're doing is we're taking 2 bromide ions and we're pushing it this way. So now I have to change a sign on that. So this is going to be negative 1.09. And so the E cell is going to be the sum of these two. So let's see, 9 and 3 is 12. Carry that, that'd be exact 2, carry that, so negative 4.02 electron volts. Now, the overall reaction here, again, you see that there's an imbalance in the number of electrons, so I'm just going to change this to be 2, 2, and 2 before I combine those 2 half reactions. That. So these guys, oh, I'll cancel those out in red just for effect, like so. And this gives me 2K plus 2 bromide ions, and this is going to produce 2K. And so that's how you do it. So you can go ahead and well, you can do it now if you want. You can pause and then come back if you like. But that's how you do those bad boys. Okay, now that is pretty straightforward. Life gets a little. Oh wait a minute. Let me put this page back. Life starts to get a little bit interesting when you add water to the system, as we do on the next page, the electrolysis of aqueous solutions, because it turns out that water itself can be a reaction, can be oxidized, and it can be reduced. So my suggestion is that first of all, you need to write down what could happen, okay, and what the reactions are going to be, whether they're oxidation reactions or reduction reactions. So this first one is done for you. I've even included all the numbers down here, but let's talk our way through this. So here I have sodium iodide dissolved in water, and give me a second. Yeah. Here I have sodium iodide dissolved in water, and so these, what you see here, are all the possible players. I'm going to highlight them a little bit more so you can see them. So there's sodium, there's iodide ion rather, and there's water. So what can happen to the sodium? Well, the only thing that sodium can do in this case, because these are say carbon rods, so they're not going to be part of the reaction. It's just this guy that can react. So the only thing that he can do is pick up an electron and become sodium, elemental sodium. So that's what you see down here. See, so Na plus 1 plus an electron becomes sodium. Now, because you're going from plus 1 to 0, this is a reduction. Okay? And if we look on the table for that, That's way down the bottom. That's negative 2.71 volts. Okay. The other player is the iodide ion. Now, the iodide ion, if you look at the table, which did it again. What did I do with that thing? I can see it through my paper, but that's because I turned it over. So, the iodide ion is right here, at 0.54. So what we're asking to do is we're saying, okay, we want to push it this way, so we want to take it from -1 to 0. So we want to oxidize this, which means that the the half cell voltage is going to be negative 0.54. So the way I've written this this time around was I wrote it in what do they call it, with the arrows indicating which way it's going to go. So here we have our first player. We have sodium, which we've already talked about. Here is the iodide ion, which is going to go back this way. This one's going to go this way. Okay, well, he can go. We don't know if he's actually going to go that way or not. Now, the other players is water. Now, in this case, because it doesn't actually say, sorry, you can't see what I'm doing here, it doesn't actually say that an acid is involved, we have to assume that this is in a neutral solution. I'm going to do this in green, and you'll see why in a second. This is in a neutral solution. Now, I suggest you do this with your, if you haven't already done this with your table, I suggest you do. Here's my doctored table, and you'll see that I have highlighted in green two water reactions. The first one here is the water oxidation reaction. Now, why do I say it's the oxidation reaction? Because it's so far at the top. Well, water lives here. And oxidation is pushing it back in this direction. So this is one thing that can happen. It can go back this way. The other place where it lives is way down here. Okay? And because it lives on this side, and it can only go this direction, this is reduction. Reduction is going from this to this side. Okay? So if I'm going to just do this, I'm going to transfer this information, these two pieces of information, I'm going to just transfer it onto our page just so that you can see kind of sort of what's happening. Okay? Oops, sorry about that. So the water here has a choice. So the water plus 2 electrons can produce hydroxide ions, and I think there's 2 of those. There should be a 2 there. Okay, and hydrogen gas. This part is reduction. So this is the reduction part of the equation. The other thing that can happen is oxidation. So this could go to 1/2 O2 plus 2H plus. This is all 10 to the negative 7 mole, which means that it's just neutral. Okay? Plus 2 electrons. Okay, this is the oxidation form. Okay, so the oxidation form, I've done it down here. As per it's written in the same way that it appears on the standard reduction potentials, except I've changed the direction of the arrow in order to indicate that it's going back that way. And I've changed the sign. It was plus 0.82 volts. Now it is negative 0.82 volts. I do the same thing with the water reduction, which is way down at the bottom here. Is that right? Or is, yeah, it's the one at the bottom. 2H2O plus 2E to 10 minus 7, negative 0.41. Now, what I've done this, I've actually been a little bit I've set this up in a certain what's the word, order on purpose. The moral of the story here is that you need one of these. You have to pick one of these. Pick one of these. Oops. And you need to pick one of these. And the question is, which ones do you pick? You want to pick the two that are closest together. Remember, one from here and one from here. Two that are closest together. And that will be this guy and this guy. And you say, well, why do you want to pick the two that are closest together? Well, because their combined voltages, so the E cell for these, the lowest one, the lowest E cell is the one that's going to go first. Like if I apply energy to it, it's what's going to happen. Okay? So in this case, what's going to happen is you're going to have one, how am I going to do this? Yeah. And this one here, 2H2O plus 2 electrons, go to H2 plus H negative. This is EO negative 0.41, so E cell is going to be negative 0.95 volts. In other words, this is what, if I put in this amount of energy, then this is what's going to happen. So probably it would have been better for me to switch this the other way around. So I'm going to redo it down here. So 2I and draw the line, cancel out the electrons. So net reaction, is going to be 2H2O plus 2 iodide ions. It's going to produce iodine plus H2 So that's the overall reaction. Okay. Now, okay, so we up the ante here, and we only up the ante in as much as that we now had to include both the water reduction potential and the water oxidation potential. And once we do that, the rest is somewhat quite similar to what we did in in the molten ionic situation. There are a few things that we want to stress. I think on the next page there's a few things. Yes. So this is the memory, or this is the like the super duper. Don't forget this. The whole point of setting up our equations as we did was to look at this. Anytime you say anything a box, that's bound to be important. So it will always be the one requiring the least voltage input. So half reactions having the greatest tendency to reduce and the greatest tendency to oxidize are preferred. Okay? Now, if they say that they are in acidic conditions, then you have to pull this back out again and say, okay, what do we do now? Well, the blue, and I'm just going to bring this in again because I want you to change your. Okay, so this is the water oxidation for acidic. Okay, so this one here. So highlight that one in blue. Okay, and the water reduction in an acidic situation is this one here. Okay. That doesn't seem right. What does it seem like? No, that's what it says. Okay. Okay. The other thing that you want to highlight is this. If you have a situation where you have chloride ion or bromide ion, just chloride or bromide, not iodide, but chloride or bromide, it will produce chlorine or bromine at the anode. So this is another important factor. Okay, how do you feel about that? Okay, I've got a note here to work through a problem or an example. So I'm going to do that, and this would be something that I would encourage you to do likewise. And okay, I need new paper. Paper 240. I gotta find it. What did it say? Is that my watch buds? Tell me to go for a walk. Tell me to take a hike. 240, 240. Now at this point, you could probably just shut me off and do this on your own, but with Hebden. But I'm going to walk through it anyway, so if I won't feel bent out of shape if you leave now. At this point, though, just so that you know where we're at, 13, I'm not sure. Finishing off the last unit, that is Hebden 5D Part 1. So questions up to 62, those should be done. I'm going to only do this part of the of 13 right now. I'm going to do electroplating and electrorefining in a different video, just because I don't want to bomb you too much, and then we'll pick it up there. Okay, so yeah, so it says what products are formed at the anode. Here's an example. Call this this is oops. This is electrolysis of an aqueous solution. Example. And what products are formed at the anode and cathode? Formed at the anode and cathode. When a solution of nickel sulfate, aqueous, so it's in water, is electrolyzed using inert, so carbon or platinum, carbon or platinum, inert electrons. Okay, so let's just make a little note here. Inert carbon or platinum. Okay, platinum is actually used widely as a as a catalyst. Okay, so what do we have in plate? We have Ni plus 2. We have SO4 minus 2, and we have two. I'm going to do a couple of spaces here, and we've got water. Okay, so Ni plus 2, that's pretty easy for him, because the only thing that he can do is gain 2 electrons and produce nickel like that. And the table for him, where would he be? I have no idea. Somebody help me here. Come on, where are you? Oh, there you are. Is negative 0.26 volts. SO4 is going to live in 2 places. SO4 is this is a neutral situation, so the sulfate ion one is going to be a bit problematic. Sulfate, I should use pencil for this. Sulfate lives in 2 places, I'm pretty sure. Yeah, here's one. So, pull this up here. Now come in. Sulfate lives here. This is one of them. But this is telling me that's in an acidic situation. And this is, there's nothing said in this question that, or this example, that suggests that it's in acidic conditions. So we're not going to use that one. The only other one is up here somewhere. Yeah, there it is, way at the top. Holy smokes. So this one here, 2SO4. So I'm going to write that down. So I'm going to do It's going to be 2. Oh, you can't see. Sorry. I should do that in pen. 2. 2 SO4 2 goes to S2O8 plus 2 electrons. So we know this guy has got to go this way, and this is reduction. So this is a reduction. I'm going to go over here. This is a reduction reaction, so that's one reduction reaction. The other one, this one here though, is going from, if you look at the table, it's going from right to left. So this is actually going to be an oxidation reaction, and I need to change its value from plus 2.01 to negative 2.01 volts, because I'm going here. Here I am here. I'm pushing it back this way, so I have to change this to negative. Okay? So that's what I've done. Oops. You can't see that. I got quality. Okay, so that's the other oxidation. Now this is the water. There's two things for water. The water reduction, so this is I'm going to put an R next to this one. So this reduction is going to be 2 of these plus 2 electrons goes to H2 plus 2 OH negative, and that's at 10 to the minus 7 more, okay. And this is negative 0.41 volts. The oxidation for this, so I'm going to put an O, water oxidation for a neutral is H2O goes to 1/2 O2 plus 2H plus, and this is at 10 to the minus 7 molar, and plus 2 electrons. And this is, it's way up here. We're pushing it back, so I have to change that to negative 0.82. So this is negative 0.82 volts. Now right now, this is too confusing to me to make a selection. So what I want to do is I want to group the reduction equations together and the oxidation one, so I can pick one of each. Okay, so I'm going to do this quickly, so you can figure it out on your own. I'm just going to do this. Okay, so first reduction is Ni plus 2 plus 2 electrons. No, I'm not going to do it that way. I'm going to do the other one. 2H2O plus 2 electrons goes to H2 plus 2OH negative 10 to the minus 7 molar. And this is negative 0.41 volts. The nickel one plus 2 plus 2 electrons goes to NiO, and this is negative 0.26. So these are the 2 reductions. I'll do the 2 oxidations. First oxidation one I'm going to do is H2O goes to 1/2 O2 plus 2H plus 10 to the minus 7 plus 2 electrons, and this is negative 0.82 volts, and the other oxidation is 2SO4, 2 minus goes to S2O8 plus 2 electrons, and this one is negative 2.0. volts. Now you should be able to see why I did it in this particular order here, is because it's easy to see the two that are closest together, and that of course is these two. Now I invite you to see what would happen if I oh, that's not true. Two that are closest together are not going to be those two. It's going to be these two, right? Nope, I was right the first time. If I add those two together, I'm going to get negative 1.08. If I do these two together, it's going to be negative 1.2. So it's these two. Okay? So these are the stars of the stars here. So I'm going to rewrite them down here. Ni plus 2 electrons goes to NiO, and this is negative 0.26 volts, and then H2O goes to 1/2 O2 plus 2H plus 10 to minus 7 molar plus 2 electrons, and this is negative 0.82 volts. So canceling out the electrons there and there, I get Ni plus 2 plus water. It's going to give me nickel plus half O2 plus 2H plus, and E cell is going to be negative 1.08 volts. Bam! Mic drop. Sorry, something. No, I can't do that. No, I can do that. Alright, how do you feel about that? Good, I hope. So let's call it a day for this. And so you can see on the bottom, oops, not that bottom. So by now you can complete homework up to 69. So you can look on Moodle. It's on Moodle. If you, I'd really encourage you to do that. Okay, but I'm running 48 minutes right now, so I think I'm going to call it, and then I will come back and we will do two of, in my mind, these are really interesting applications of electrolysis, and I love these ones, and I don't think there's any calculations involved in this. Maybe there is. Oh yeah, maybe there is, but it's stuff that you've already had. Okay, well, I'll see you back shortly, and yeah, if you come back tomorrow, so much the better. Love you. Bye now.